Okay, so in the last video, we started talking about the concept of polarization. And remember, polarization can only occur with transverse waves. And when we talk about a transverse wave being polarized, we basically mean that its direction of oscillation is restricted to only one plane. Okay, so today we're going to finish up this unit talking about polarization and go into more detail. Okay, now, even though any transverse wave can be polarized, we're mainly going to focus on polarization of electromagnetic waves because that's where the most interesting applications are. Okay, so let's kind of back up a little bit. So electromagnetic waves are produced basically by oscillating charge. So if you have a light source that has that produces light in kind of like a random manner, like the sun or a light bulb, then you get what's called unpolarized light. And by unpolarized light, I mean light that consists of many different electromagnetic waves all oscillating in a different plane. Okay, and so that's what's called unpolarized light. Now, again, when we talk about light being polarized, we talk about in some way making it restricted to only oscillate in one direction. And there's a few different ways to do that. We're mainly going to talk about a material called polarizer, but light can also be polarized through reflection across different surfaces. And we'll also talk about that as well. Okay, so a light source, like I said, the ceiling or light from the sun, that light tends to be unpolarized. Light from some light sources is polarized, like I believe laser beams are polarized light. Your computer monitor, if you have an LCD computer monitor, that light tends to be polarized as well, which is why if you have polarized sunglasses and you're trying to look at the computer monitor, if you turn your head, you can see the screen get darker for that reason. Okay, so again, light is said to be unpolarized in the sense that the electric field parts of all the different electromagnetic waves in a beam of light are all oscillating in different directions. Okay, so that's what's called unpolarized light. Now there is a material, it's a man-made material called Polaroid, which can take unpolarized light and basically only allow through light that is polarized in a certain plane. Okay, and this this film again is called Polaroid. I will link later on a video that goes into more detail about how that material works. It basically has to do, well, I'll let them explain that in the video, but it's kind of an interesting thing. Okay, so light that comes through this filter is all oscillating in the same direction, in the same plane, and therefore is said to be polarized. Okay, specifically, the electric field components of those electromagnetic waves are all oscillating in the same direction. Okay, remember when we talk about polarization, we're mainly talking about the electric field being polarized. Okay, so you can imagine it kind of like a filter, if you will, where if you have unpolarized light come into the filter, anything that comes out the other side is automatically polarized in a certain direction. Okay, so here we kind of have a diagram. Here on the left side we have unpolarized light. Okay, unpolarized in the sense that it consists of a beam that has a bunch of different electromagnetic waves all oscillating in different planes, and anything that goes through the film comes out lined up with what's called the transmission axis of the Polaroid film, and therefore is all polarized in the same direction. Okay, and so I would say this light that comes out on the right over here is polarized up and down. Okay, so pause there if you need to look at that some more. Again, I cannot emphasize this is not the only way to polarize light. You do also need to be aware that light that reflects off of certain surfaces can become polarized. That's kind of how polarized sunglasses work. They reduce glare because if you're looking at the concrete on a hot day and there's a bunch of glare on the road and you're driving and it's hard to see exactly, what happens is the sunlight that comes and hits the road, and as it reflects off the road, it becomes polarized. And so those sunglasses are designed to basically remove those polarized reflections because they're polarized in a direction that doesn't get through the filter in the sunglasses. Okay, so without going into too much detail, because we'll see a video later that more explains how this substance works. It basically polarizes a film made of very long parallel molecules, and it only allows certain types of electromagnetic waves through that are oscillating in a certain plane. Okay, so these are just kind of pictures showing how, unpolarized light going through a polarizer would become polarized. And this is just a diagram showing the same thing. Here's a light bulb, here's the light that goes in, it's unpolarized, it goes through the piece of Polaroid film, comes out, and it's all restricted. Okay, it's all oscillating. And if it helps you to think of kind of this situation, obviously it's not exactly like a physical filter like this, but if this kind of analogy of like a rope being allowed to move up and down, if the slits are like this, but it can't move side to side, if that helps you understand the concept of polarization, then that's something that might be helpful for you to think of. Now, the interesting thing is, though, is if you have light, let's say you have unpolarized light, it goes through a polarizer, and let's say it all becomes polarized up and down. Okay, if you have a second filter that is turned 90 degrees from the first, then what happens is nothing gets through that second filter. Okay, and the reason is kind of obvious if you're looking at the slit. Here in this second picture, down here you can see this wave comes in, it goes through this first slot in the fence, and it's polarized up and down. When it gets to the second one, because these slots are horizontal, the wave on the string can't get through. And a similar thing happens with polarized light. Here you can see, this is obviously just like not a real diagram, but you can see a demonstration of this on the next slide. But if you take two pieces of Polaroid, if you turn them 90 degrees to each other, then the light becomes, or the film becomes dark because no light is able to get through this. Okay, and I will try to do this demonstration for you guys if I get the opportunity to, because it's really cool to see in real life. But as you hold the two films up, as you turn one relative to the other, you can see the intensity of the light that makes it through changes. And if they're 90 degrees to each other, then almost none of the light gets through. Okay, so here I'm going to link a video demonstration of what I just described. Okay, and then I'm going to kind of go along here. Just a terminology thing that you need to be aware of, just in case you see this word in problems. A lot of the time on IB questions, in situations where you have two polarizers, the first one is usually called a polarizer, and the second one is sometimes called an analyzer. I don't know why exactly, that's just the terminology that the IB uses. It's not that one is different than the other. It's just typically whichever one comes second in the problem is called the analyzer. Okay, so if you ever see that terminology, an analyzer is just another polarizer that happens to be before or come after the first one. Okay, now as you probably saw in the demonstration video, the intensity of the light that gets through the analyzer changes as you kind of rotate that second piece of film. And so what we're going to talk about here in a minute is how to mathematically describe that change in intensity. Before we do that, just some really quick applications of polarization. One of the most common examples of polarization that people experience every day is using polarized sunglasses. We talked about that before. When light hits the road while you're driving, it can cause a lot of glare on the road when it's really bright outside, but that light, as it reflects off the road, is horizontally polarized. And so if you have sunglasses where the transmission axis is vertical, that means it only allows light through that's polarized up and down. When the light that's polarized horizontally tries to go through those sunglasses, it doesn't make it, and so you don't see that light, which means that you don't see the glare. Okay, and so that's how polarized sunglasses can reduce glare. Again, I don't want you to think that light, or that this Polaroid film thing is the only way for light to be polarized. It can also happen off of reflection from different surfaces, like you see here. Okay, unpolarized light comes in from the sun, hits the water, reflects into this guy's eyes, and when it reflects off the water, it's horizontally polarized. Okay, and so what I'm going to do now is I'm just going to link some videos for you to check out having to do with the concept of polarization. The first one is just kind of a good overview of how polarization works, along with how polarized sunglasses work. The second one as well talks about that. Don't feel compelled to watch, every single one of these videos all the way through, unless you just find them really interesting. But some of these really are interesting. I would definitely encourage you to at least watch the first one. At least the first maybe couple of minutes of the second one. This how LCD displays work is also a really interesting video. I would highly encourage you to watch that video, because I don't know if you're aware, but LCD screens like your computer monitor, your laptop monitor, some TVs are called what's called LCDs, which is liquid crystal displays, and those work based off of the property of polarization that they talk about in that video. Okay, so a lot of applications of polarizations. So I will link all of those videos in. Again, I would highly encourage you to at least watch the first 2 or 3 videos, but this is some really interesting stuff. Okay, so the rest of this video is going to be about what's called Malus's Law. Okay, now, a couple things about Malus's Law. We know that light that is polarized, when it goes through a second polarizer, aka an analyzer, the intensity is reduced, okay, based off of the angle between those 2 transmission axes. If it's an angle of 90 degrees, then obviously no light gets through the analyzer. We talked about that before. If the 2 transmission axes are perpendicular to each other with a 90-degree angle, then no light gets through. Now, to mathematically describe that, we have what's called Malus's Law. Before we talk about Malus's Law, something that has nothing to do with Malus's Law really, but just a fact that you need to know is this. Unpolarized light that passes through a polarizer will have its intensity reduced by half. Now you're about to see Malus's Law. That's one of the equations given to you in the data booklet. The fact I just said has nothing to do with Malus's Law. This is just something that you need to make sure that you're aware of. It's important that you understand that Malus's Law only applies for light that has already been polarized. So you have to be really careful when you're reading problems, and you have to understand, is the light in the problem unpolarized or is it polarized? Okay, because which one it is depends on how you handle the problem. Okay, so to describe how the intensity of already polarized light passing through a polarizer changes, we have what's called Malus's Law. Okay, so here we have just a picture of unpolarized light becoming polarized. Just a repeating of the fact that I said unpolarized light loses half of its intensity when passing through a polarizer. Now we get to Malus's Law. Once the light is already polarized and we're going through a second one, an analyzer, now we get to Malus's Law. Here's how Malus's Law works. Now I'll try to make this picture a little bit bigger. First of all, Malus's Law, so Malus's Law, the equation for Malus's Law is in red up here. It is I equals I naught times cosine squared theta. So let's try to understand what this law is saying. Let's say we have a situation where we have unpolarized light from some source. It goes through a polarizer, its intensity is reduced by half, whatever. Okay. This part has nothing to do with Malus's Law. Once we have light that is already polarized and is going through an analyzer, then Malus's Law takes over. Okay. I naught, or I0, whatever you want to call it, is the intensity of the light that has already been polarized going into the analyzer. Okay. I, in the equation, is the intensity of the light coming out of the analyzer. Okay. So this is going in, this is coming out of the analyzer. Okay. Notice, by the way, this I naught, that's not the intensity of the original light, because the intensity of the original light was actually 2I naught, and when it went through the first polarizer, it had its intensity reduced by half. Okay, so I naught is the intensity of the polarized light going into the analyzer. Theta is the angle between the transmission axis of the polarizer and the transmission axis of the analyzer. Okay, so in other words, if the polarizer and analyzer were both perfectly aligned, let's say they were both pointed straight up and down, that angle would be 0 degrees. Cosine of 0 degrees is 1. And so if that was the case, the intensity in and the intensity out would be the same. Okay. Now, what if they were turned 90 degrees to each other? Then cosine of 90 degrees is 0, and I would be 0. By the way, one of you, or some of you might be thinking, wait, didn't he say something about the intensity being reduced by half? Why would it be the same if theta was 0? Remember, it's only reduced by half when it's unpolarized light becoming polarized to begin with. If you have light that's already polarized and it's going into an analyzer and the angle between those two is 0, that doesn't affect the intensity. Okay, it's only reduced by half when it's going from unpolarized to polarized. Okay, so if theta was 0 here, then I and I naught would be the same. They would be equal. Okay, so that is Malus's law. Pause it there if you need to look at that. Okay, so let's just do some quick examples. Okay, so example 1, I guess, state what is meant by polarized light. Okay, so pause it here and try to answer this question on your own. Alright. Okay, so polarized light is light whose waves have their electric fields oriented in one direction. Now, I've seen this question show up sometimes on IB exams, and almost always you have to specifically refer to the electric field of these electromagnetic waves being forced to oscillate in only one direction. Okay. A lot of the time people will say, light passes through a filter or whatever. No, that's not what polarized light is, because remember that there's other ways to polarize light besides Polaroid. Okay, you can polarize it through reflection or other sources. Okay, it's light whose electromagnetic waves have their electric fields. You have to specify the electric field forced to orient in only one direction, or forced to oscillate in only one plane. Okay, let's do another question. Polarized light of intensity I naught is instant on an analyzer. By the way, if you don't know what that word is instant means, this basically means hits. Okay, light of intensity I naught hits an analyzer. The transmission axis of the analyzer makes an angle theta with the direction of the electric field of the light. Calculate in terms of I naught the intensity of light transmitted through the analyzer when theta equals 60 degrees. This shows up a lot on IB questions in terms of. Okay, when it says in terms of anything, that means the answer to the question should contain that thing. So in other words, we should have an answer at the end of this question. We should have an answer that is something, 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 I naught. Okay, some multiple of I naught. That's what in terms of means. Now in this case, this is just a Malus's law question because we have light that has already been polarized. Okay, therefore this is a Malus's law question. And we're given theta equals 60 degrees. Now you don't need to know this off the top of your head because you would be able to use a calculator on this question, but it would help you, of course, if you happen to know that cosine of, let me put the 60 degrees in, cosine of 60 degrees is 1/2. And so if you do cosine squared, 1/2 squared is 1/4. And so I would be I naught over 4. So in other words, this would be the answer to the question. Okay, because it says in terms of I naught. The answer is not 1/4, it's 1/4 times I naught. A really easy Malus's law question. Pause it there if you need to look at that. Okay. Just a couple more examples. Calculate the rotation angle needed to half the intensity from its original value. Okay, so if we want number one, we don't know what the angle is. That's what we're asked to find. But we want to half the intensity of polarized light from its original value. What that means mathematically is we want I to be I0 divided by 2. So we want the angle that's going to make that happen. So here's how we do this. We have Malus's law. I'm going to plug in, for I'm going to plug in I0 over 2 because we want the angle that's going to cause the intensity to be reduced by half. Notice because there's an I0 on both sides of the equation, it actually cancels out. And so what I get is 1/2 equals cosine squared theta. Okay, I want theta by itself, but it's stuck inside a cosine squared. I need to get rid of the squared first. So I take the square root of both sides. So I have the square root of 1 over 2 is equal to cosine theta. And then to get theta by itself, I have to take the inverse cosine of both sides. Okay, so the inverse cosine of the square root of 1/2 is equal to theta. And if you put that into your calculator, then you will get the answer. Okay, so I'm going to do that really quickly. Although I will say this is one of those questions that is pretty easy to answer if you just understand the concept of what's going on. So inverse cosine of that angle, I get theta equals 45 degrees. Now, if you think about it, that should make complete sense, because at 90 degrees, the intensity would be 0. At 0 degrees, it would all get through. So it probably makes sense to you that, if the angle is 45, that's halfway between 0 and 90 degrees, half of the intensity would get through. Okay, so maybe some common sense there. Pause it there if you need to look at that. Okay, and just one or two more quick examples. Here is another example. Unpolarized light of intensity 40 watts per square meter is incident upon a polarizer and an analyzer. The analyzer is turned so its transmission axis is at a 30-degree angle to that of the polarizer. Calculate the intensity of the light which enters the analyzer. Okay, now you have to think very carefully. Unpolarized light goes through a polarizer, becomes polarized, and automatically has its intensity reduced by half. That has nothing to do with Malus's law. That's just how it goes. So how much light goes into the analyzer is 20 watts per square meter. Now in Malus's law, that is going to be I0. Because remember, I0 is the intensity going into the analyzer of light that's already been polarized. Calculate the analyzer angle, which would result in light with an intensity of 5 watts per square meter leaving the analyzer. Okay, so here again we're looking for theta. Okay, I is the intensity leaving the analyzer. So if I just plug in these values, I get 5 equals 20 times cosine squared theta. 5 over 20 is 1/4 equals cosine squared theta. I would take the square root of both sides. The square root of 1/4 is 1/2. And then I would do the inverse cosine of both sides. And so theta would equal the inverse cosine of 1/2. Now, of course, I already know what that is because I know that the cosine of 60 degrees is 1/2. And so theta would be 60 there. Now, if you're reading the question carefully, you're probably wondering what that 30-degree angle that was given in the problem had to do with anything. Nothing at all. I honestly don't know why it was in there, but based off of the questions we're asked, it doesn't have anything to do with anything. Okay, so pause there if you need to look at that. And then I think just one more quick question. polarized light of intensity I0 is incident on an analyzer. The transmission axis of the analyzer makes an angle theta with the direction of the electric field of the light. On the axes below, sketch a graph to show the variation with angle theta of the intensity of the transmitted light. Now it's very, very important that you understand the concepts involved here and you understand clearly what you're given in the question. I0 is the intensity of polarized light and it's going into an analyzer. If this was unpolarized light going into a polarizer, that would be completely different because then the intensity would just be cut by half, right? Here, the light's already been polarized. That intensity is I0. And the easiest way to approach this question is just to stick with the points that you know have to be true and then kind of fill in the blanks. Okay, now we know that when theta is 0 degrees, the intensity is equal to I0. Right, because Malus' law says I equals I0 cosine squared theta. When theta is 0, or cosine of 0 is 1, and so these two are equal. Same thing with 180 degrees. Cosine of 180 is -1, but when you square it, it becomes +1. Okay, so I know that the intensity would also be I0 here. When theta is 90 degrees, okay, I is going to be 0. And so I would want to sketch a graph that kind of tries to go through those points. This is really hard to do well with a pen on a tablet, but something kind of like that goes through those points. Now, honestly, the type of graph this is just a cosine squared graph. I guess if I click forward, you'll see a better version of the graph. Here, they may be adding in more points than I would have done, but the graph should look something like this. Okay, so you do sometimes see problems where you have to sketch that. Okay, and then this last one I'll just kind of show you. Okay, so pause there if you want to look at that answer some more. Okay, so you have a polarization practice worksheet. You also have polarization questions and Malus Law questions on your topic 4 part 1 worksheet. We are done with this unit. That is the last thing in 4.3 is polarization and Malus Law. As always, please let me know if you have any questions, and I'll see you guys in the next video.